In this short ANSYS Innovation course video, we'll be comparing two of our material families together, ceramics and glasses. Now, the reason we group these together is because technically both of them can be considered ceramics. So why do we bother separating them in the first place? To understand this, we've got to do a deep dive into the atoms that make up these materials and how they're bonded together. Let's take an example of fused silica glass and quartz. Fused silica glass is great for high temperature applications as it has very high thermal resistance and it's resistant to thermal shock, or when you heat something up rapidly, it won't break. Quartz, on the other hand, is a piezoelectric. That means when I apply a mechanical force or load to the material, an electric potential forms. Quartz is what keeps your analog watches ticking. Why do I want to compare these two materials together? Well, they're both made of silica, or SiO2, but they have such different properties. That's because quartz is crystalline, meaning it has a long-range, repeating 3D periodic arrangement of the atoms, ions, or molecules that make up the material. Fused silica glass, on the other hand, is amorphous, meaning it lacks this long-range order. One of the properties that changes between crystalline and amorphous materials is how they solidify. Crystalline materials act as you might expect. We reach a temperature, and the phase change occurs. For amorphous materials like glass, however, it's a much more gradual process. As the liquid slowly cools and becomes more viscous or thicker, eventually it will go through a final glass transition temperature, where the supercooled liquid officially solidifies. That's why so many people consider glass to be technically still a liquid. It's a solid, I promise. It just behaves a little bit differently. So now that we have this baseline, we can talk about ceramics and glasses and compare them to one another. Let's first start with ceramics. They're some of the oldest engineering materials we as humans used. Think of walking through a museum or pictures from an archaeological dig. There's pottery and porcelain everywhere. Think of ancient monuments. They're built from stone and marble, not only because of its beauty, but because of its structural integrity. We're still using these ceramics for large buildings and homewares alike. For example, I have this ceramic bowl that I use when I have company over to hold chips, dip, and other appetizers. Let's compare ceramics to the field of materials as a whole through our Ashby charts. We'll be talking about two different subcategories of ceramics here: non-technical, like the marble or stone that I talked about earlier, and technical ceramics, which are used in more advanced settings. Ceramics as a whole are both stiff and dense. The bowl I own is heavier than it looks, and it's not easily bent. Ceramics used in ancient times have low fracture toughness. Link in The Legend of Zelda is known for his affinity for shattering pottery. Not all modern-day ceramics are this fragile. As our understanding of ceramic structure and processing capabilities have grown, we can now manufacture ceramics with better fracture resistance. As a whole, however, they're still considered quite brittle. Their strength can still vary widely and again has improved as time's gone on. Ceramics generally have high electrical resistivity, but can have a range of thermal conductivities. This is why coffee mugs are generally made out of ceramics. It'll keep your hot drink warmer for longer, even if you forget about it on your desk. Not all ceramics are used for buildings and homeware. Some ceramics have very advanced applications, say space shuttles. We know that entering and exiting the atmosphere is extremely hot. We need to make sure that the outside of our space shuttle can withstand these high temperatures, but the people inside don't feel those hot temperatures. To do this, the outside of space shuttles are covered with these ceramic tiles. They're so thermally insulating that they protect the astronauts from the heat of exiting and entering the atmosphere. These tiles are so good, you can hold a blowtorch underneath one, place a flower on top, and the flower won't burn. Let's switch gears now to talk about glasses. If we're thinking historically, as we as humans started to use more and more materials, our ability to process materials at higher and higher temperatures increased. This allowed us to start processing glasses, which have a very high melting temperature. But Processing materials at this high temperature takes a lot of energy and a lot of skill. That's why glass was, and still can be, quite expensive, and historically was used for very special occasions and very decorative pieces. It's still used for decorative pieces today, like this vase I have, for example, when I want to show off a bouquet of flowers around my house. Glasses, similar to ceramics, are stiff and dense. This similarity makes sense, since they both fall under the same parent category of ceramics. Glasses, again similar to ceramics, are quite fragile and not very strong. Perhaps some of you watching have experience with breaking a drinking glass. Sometimes this seems to happen with not that much force. Just a single tap and crack. Glasses have high electrical resistivity, but have decent thermal conductivity. Think of pouring a hot drink into a glass cup. You can certainly feel the heat of the drink through the cup. While the examples of glass I've given so far have been homewares, there are some very advanced applications of glass. One that you might be familiar with is your car windshield. If we think of a plate glass window breaking, it's going to break into really large, sharp shards of glass. This is the last thing I want during an accident. There's already enough debris flying around that could injure the passengers of the car. To avoid this, the glass made in windshields is called tempered glass. Tempered glass is processed by cooling the glass very rapidly, so the surface of the piece of glass solidifies more quickly than the center. Because materials shrink as they solidify, this is applying a compressive or pressing in on the still liquid center of the glass. As the liquid center is cooling, it is opposing this compressive force with a tensile force, which means it's pushing out. These balanced forces mean that the glass is much stronger than it was originally, and when it breaks, it will shatter into small pieces. Imagine if I'm pushing on something. If I remove one of the forces, well, now all the energy has been released. So you can see that there's been a lot of engineering to make all aspects of cars safer, including the car windshield. So now we've covered some of the basics of ceramics and glasses. Next, we'll move on to the metals material family.